Thank you, Harold. Thank you all for being here. It's a great honor and pleasure for me to chair this session, which will have three excellent talks. And without further ado, I want to introduce the first speaker, who is very well known for his work in general relativity, black holes, cyclical conformal cosmology, predicting eons before the Big Bang. And last but not least, his pioneering work in consciousness studies, which helped launch the resurgence in the 1990s of consciousness studies with his great 1989 book, The Emperor's New Mind. So please welcome Sir Roger Penrose.
Well, thank you very much. This isn't exactly the title to my talk, but it will do. And I apologize that I'm not using overhead projector because they're getting too heavy for me to carry around. Anyway, that isn't the title, but it'll do. First of all, I want to describe what I'm going to talk about. I'm going to talk about consciousness, but only in a very particular sense. And I won't read my slides because I can't very well see them, so it's all right if you read them. But the gist of it is that there are various things that one can talk about consciousness. My particular view is that consciousness depends on physics, and it depends on a physics which we don't yet know. The main thing I will concentrate on is not all sorts of things that other people talk about when they talk about consciousness, such as things as, perception of the color blue or feeling happy or all sorts of other things. The thing that I will talk about is specifically understanding. So I have three words here on the screen. I hope I can... No, I've gone too far. Yes, I have to press this button. Here we go. I have the word awareness, I have the word understanding, and I have the word intelligence. And the idea is that real intelligence, I'm not sure about artificial intelligence, but real intelligence, understanding is necessary for it, because you wouldn't normally think of an entity that is really intelligent if it possesses no understanding. That's the normal usage of language. And I'd also say that an entity which has understanding and has no awareness, that doesn't make any sense either. So that awareness is an essential feature of understanding. So I'm concentrating on the one word, understanding, and the question is whether our current ideas of a computer, that is a digital computer, a computer which operates according to our notions of algorithms, discrete algorithms, whether such a device could possess understanding. So this is the issue which I'm going to talk about. And let's continue with the pictures. Now, people know nowadays that computers can do wonderful things with the game of chess. They can beat grandmasters and so on. So the computational system Fritz can beat grandmasters and all this. Well, I constructed a few years ago this chess position, which is specifically designed that a human being looking at it, and you don't have to know much about chess, can deduce pretty quickly that it's a draw. You see that there are several black pieces which are trapped in the corner up at the top. Let's see, I have to make sure I press the right button. No, I pressed the wrong button, sorry. I'm not very good at these things. Why is it not going backwards? Oh, here. Yes, there's the chess position. It seems to have shrunk. If you can extend it to the whole picture. I don't know what happened. Did I press something? Yes, thank you. Yes. I must be careful about the buttons here. Now, you see, it looks as though black has a considerable advantage. It's got two extra bishops, or three extra bishops, and an extra knight. And so I have no idea, really, how the machine calculates who's winning or not. I assumed that it probably plays lots and lots of moves and tries different moves and all that sort of stuff. If I go there, he goes there. If I go here, he goes there. And then it has to assess whether the position is improved or not. And how does it do that? Well, I guess by counting the pieces and seeing how many pieces of bigger value there are. And so this would be considered to be a win for black, although if you know anything about chess, you will realize that these pieces can't get out. You also realize that there are 3 black bishops on the same color. That's not an illegal position. It's an unusual one because you have to bishop a few pawns instead of queening them. To get to this position, you would have to be completely stupid. So both players would have to be completely stupid to arrive at this position. And that's part of the point. So this would not be part of the computer's experience. And what does it do? Well, I predicted that it would lose. That is to say that the black would lose. In fact, it does. You give it to Fritz at grandmaster level, it loses. Why does it lose? Well, it loses because it estimates, by counting the pieces of something, that it's a win for black, which you can see is nonsense because the black piece can't do anything. Can't attack the pawns, the one that's running around, the black bishop can't do that, and so on. So it's clearly not a win for black, but that's the estimate it makes. And so then it plays up to 30 moves, I think that's 30 each, until it comes to the point where if a pawn is not moved and the piece is not taken, then it's a draw. And since black estimates that it's a win for black, it's got to do something desperate. And what it does in this position is sacrifices its bishop. Sacrifices the bishop, the white king can take the other pawns, they can march up, make 2 queens, and it can checkmate after quite a few moves. And so it's stupid. Okay, that's an example which seems to indicate that despite how good Fritz is at beating grandmasters, it hasn't the faintest idea about the game of chess, which is slightly paradoxical, but nevertheless. Then I started wondering about the game of Go. So I thought of making up a position like this, but I sort of gave up after a while. I thought of another idea. The other idea is that you see, in the game of Go, you start with an empty board, and then black puts a stone on, then a white puts a stone on, then black, white, like that. And there's this thing called AlphaGo, which beat the best Go players, and then there was an Alpha, whatever it's called, AlphaZero, which beat AlphaGo, and it also beat all the players, and so on. So the question is now whether AlphaZero actually understands the game of Go. Well, the idea I had was instead of starting with an empty board, you start with some stupid position at the beginning, completely stupid position that would never have been come across in the experience. I mean, this thing plays, I don't know, zillions and zillions of games against itself, but does it ever come across a position like one of these? So these are just examples. I can think of a lot better ones, actually. These are the sort of positions you could start with, never come across in the ordinary game of Go, completely stupid positions. And so the experience that the Alpha, whatever it is, AlphaZero has, would not be based on positions like this. It would never have come across them. That's the idea. I don't know. But the idea is to have a competition. You would have a lot of positions like this, some better ones, and you present for the first time, the computer and the human, neither would have seen the position before, and get them to play against each other on even terms, apart from the fact they've got unknown positions. And since these are not part of the experience of the Go machine, my guess is that the human would win. It'd be very interesting to see if that's the case. Anyway, that's a project which is apparently going to be taken up seriously, and the idea is that maybe this will, before too many months, it will be set up, and perhaps a good Go player against the Go machine, and see whether the human might actually beat it under these circumstances. It will be fascinating to see. Anyway, what about this one? This is another proposal that I'm wondering about how a computer would do. I understand that in the Go AlphaZero, it gains its experience from pattern recognition. So it sort of gets a feeling is the wrong word because I'm claiming it doesn't have any experiences, but nevertheless, it gets the impression in some sense that certain configurations are more likely to be better than others without having any understanding of why. But the fact, it just goes through all these zillions of different possible positions. And this is another thing you could try like this. So you give these 3 shapes. That's a square, a hexagon, let's see, a square here and a hexagon and a dodecagon, regular, and but they're marked with these arcs. And you have to, when you put them together, you have to mark them, you have to make the marks agree. And the point is that you start with the dodecagon, and then you put the other pieces around it, and make as big a region as you can. And so you then program the computer to fit these together so it fits, and see how big a region it would make. And this, I think, will be an interesting test for a computer. And let me show you the sort of pictures that you have to end up with. I should say it's well, let me go to the next slide. That's the sort of pattern it makes. You see there are a lot of patterns there which you might imagine the machine would get used to the pattern recognition or something. I wonder whether it would get it very far. It will only tile the plane in a non-periodic way, and there you see an example. If you look carefully, you can see the hexagons and the dodecagons and so on behind. And here is another one, which is more refined. Now, could it make a pattern just by trying, maybe using pattern recognition or something like that? Could it make a pattern that big? I would think it's a bit unlikely. I should say, of course, this particular picture was drawn by a computer, but it was drawn by a computer with a specific algorithm which tells you what the pattern is. But that's not the test. You would give this to a machine which has no idea the idea behind the tiling, and it just tries all possibilities. Maybe it likes certain arrangements in preference to others. I don't know how you do it. It would be very interesting to see whether it could even get that far. I'd be very surprised if it could. Anyway, that's another test, which would be a test to see whether, even though the computers can do very well, do they understand anything? And the argument that I'm making is that they don't have any understanding whatsoever, and that they don't have any consciousness. So this was the kind of argument that I play with. Now, I should say that these things are really finite problems, although the tiling one is basically an infinite one, because you can prove that you could tile the whole plane, but how far you can get by trial and error is another question. But in mathematical problems, you see, the game of chess or the game of Go, they're finite games. So you might imagine that eventually they could be worked out from start to finish. And then there would be no chance in defeating it in any way, not even by the ideas that I have. But if you want to talk about really testing understanding, what I claim to do, you need to talk about the infinite. Now, people often think, well, infinite, you can't really think about the infinite. That's certainly wrong. I mean, for example, if you take two even numbers and add them, you always get another even number. That's a statement about the infinite. So we can certainly have conceptions, reliable conceptions about the infinite. That's not a problem. There's a sort of standard way in which we talk about the infinite, and in fact the whole idea of a Turing machine, on which you might say the modern computer is based, in a certain sense, certainly, these machines have a certain way of dealing with the infinite. And this is a cartoon which really explains the Turing machine in a certain sense. The Turing machine is the thing in the middle here, which is a finite little thing. It's got a certain number of states and all that, but it's got an infinite tape. This was Turing's original concept, and it's an unlimited tape, let's call it. To do a computation, it would use a finite amount of the tape, but you can't tell necessarily how much of it uses. So this is the idea of a computer. You've got a finite device which does the computing, but a potentially infinite store. Well, in practice, you can't have actually infinite, but you can certainly have very big storage. But this is the sort of way in which you talk about computations in mathematics. See, my idea of saying understanding, it's understanding in the very limited sense. It's an understanding of mathematics. Now, that is, of course, understanding goes much more broadly than that. I'm not trying to say that there's something special about mathematics. It's just that mathematics, you can make definite statements, and that's hard to make definite statements about other things. And these definite statements can tell you that understanding in mathematics is not an algorithmic process. So let me try and explain well, first of all, let me say how in mathematics there's a standard procedure that one learns at school about how to talk about infinite things. So I hope that's my next slide, because it's meant to be. Yes, this is mathematical induction. Suppose you have a statement which depends upon a natural number, a positive non-negative integer. So you have a proposition which depends on a number. And you want to know whether that's true for all n, that n is the number. Well, mathematical induction is to say, establish it for n equals 0. That's one thing. Establish it that if it's true for n, then it's true for n plus 1, and that establishes it's true for all n. And that's the standard way of proving something for all numbers, for all integer, positive integer, natural number, non-negative integer numbers. And you can make this into a computation. How do you... you can make a computer which decides things which can be proved this way. Now, the trouble with this sort of thing, and this is what started me off in my line of thinking about why human understanding is not a computation, was from this famous theorem of Gödel. Now, this is actually not, I'm going to talk about it not in Gödel's original form, but Turing's form. So I put Turing up there now. This is Turing's form of Gödel's theorem. Now, this states the following. Suppose you have a set of rules, R, which you could put on a computer, and these rules chug away, and you give it another statement. You're going to give it a particular statement. So you say, is the following true or not? And it's got to be a thing about, say, numbers. It could be, for example, Goldbach's conjecture, is every number greater than 2 the sum of 2 prime numbers? Well, for that particular one, it would chug away forever and not give you an answer. At least as far as we know, I don't know. That's not definitely clear. But the thing is that if the thing does give you an answer, these rules have to be such that you trust them. So if it does follow the rules and gives you the answer yes, then you have to believe the statement that you fed in. So you put in this mathematical proposition, set the rules on that proposition, and see whether the machine can prove it using these rules. And the first point is you have to trust the rules. Now, why do you trust the rules? Well, you look at them. You look at rule number 1 and you say, yeah, I think that's okay. Sure, I believe that. Then you look at number 2 and you say, oh, yes, that's okay. That's fine. Look at rule number 3 and so on. You go all the way through and you say, they're fine. We accept that anything that the machine does which comes up with the answer yes, then it is a true statement. Now, what Gödel does is something which I've found absolutely stunning when I first heard about it, is you construct a particular statement based on the rules that this thing I'm calling G of R here, that particular statement which you can see by the way it's constructed that if you believe that the rules R only give you truths, then G of R must be a true statement. But also must be a statement, when you see what it means, a statement which is beyond the scope of R itself. So this tells you that your belief in the rules or your understanding of the rules enables you to transcend the rules. So using the rules gets you so far, but knowing why the rules work gives you more than the rules, using the rules themselves. When I learned about that, I was blown completely, my mind was blown. I thought, that's absolutely stunning. It tells us that if you know the rules according to which we understand mathematics, then we can transcend them. And so therefore, those rules, if they're computational rules, we can't know them, whatever it is. And the argument basically is to show that we don't act according to rules. Well, there is a question here. Maybe we've got an algorithm in our heads which we don't know. And that would be hard to use this argument to demonstrate that things that go beyond those rules. So I use this example. This is a cartoon. It somehow got reflected right, left. I don't mind that. When I put some words up, they're a little more serious. So let's see. It's all right. The words are not reflected, so that's okay. You see, this is supposed to be a cartoon illustrating how natural selection might have given us understanding of mathematics. And I've got in the foreground this poor mathematician who's struggling with a geometrical theorem, and he's about to be eaten by the saber-toothed tiger over here, you see. So he's not very well selective advantage in doing mathematics isn't very much, you see. Whereas his cousins, which are building they're domesticating animals, they're building shelters, they're harvesting crops and sort of thing. In the foreground, you see they're building a mammoth trap, and they're doing all sorts of things with their understanding, yes, and that's no doubt what was selected for by natural selection. But being able to do sophisticated mathematics, no. Maybe natural selection would have been good enough to give us the law of what I just described, mathematical induction. So you might imagine that somehow understanding mathematical induction would have been a selective advantage. I think you could argue about that. But what about the things that go beyond it? And sometimes, if I have enough time, I give you an example of a thing called Goodstein's theorem, which is an example of a Gödel statement. In fact, it's a Gödel statement for mathematical induction. So we know it's true because we know to trust mathematical induction. But we don't know that it's true by virtue of mathematical induction. In fact, it's a proof of a theorem by Paris and Kirby, where they showed that this particular Goodstein theorem is not provable mathematical induction. Nevertheless, you can see, with a little argument, you can see why it's true. Now, why it is true could not have been naturally selected. I can't see how it could have been naturally selected at all. Even if natural selection was good enough to give us the induction principle, it wouldn't have given us anything beyond that. So that's the argument which I've gone on with for a long time. Now you see, where do we go from there? Well, I would try to argue that, this is just to show natural selection isn't going to help for human beings. But the question is, okay, I'm talking about mathematics in a particular context, and I'm trying to say that that is not computationally simulable. You can't make a computer which imitates human understanding in mathematics. But there's nothing special about mathematics. I'm certainly not arguing that it's just mathematics or something. I don't think there's a line between that and understanding generally. I don't think there's a line between human understanding or animal understanding. And now from what we've been hearing earlier in this session, what about plant understanding? I'm not sure. Well, how far down it goes, I have no idea. I don't think it's restricted to humans, certainly. But is it animals? I don't know. Or is it particular kinds of animals? I don't know. But the point is that this is a quality that seems to be part of our construction. Now, I do hold the view that whatever is going on in our brains is part of the physical world. And this was when I started thinking about these things when I was a graduate student in Cambridge, and I went to several lectures. One was a lecture on Gödel's theorem and Turing machines, and another was on general relativity, and another was on quantum mechanics. And so I got the impression about, okay, you can put general relativity on a computer. You can, in fact, we know now from the observations of gravitational wave detection from the LIGO gravitational wave detector, and the one in Europe, the Virgo, that you can see that there are black holes spiraling into each other, and the very clear signals that this produces as the result of lots of very complicated computations. So this illustrates how general relativity you can put on a computer. What about quantum mechanics? See, these are the two great theories of 20th century physics. Well, quantum mechanics consists of two parts. And I think I'll go to the next picture if I can do this right. Don't worry about the details here. I just want to illustrate that quantum mechanics, the top, I'm just having two sorts of experiments. One illustrates the particle nature of you imagine this laser at the top left, and it shoots a particle at this half-silvered mirror, and it goes one way or the other. But if you have this more complicated situation where it goes both ways at once, then you get interference effects. So you have the particle nature of a particle in the first one and the wave nature of the second one. And the wave nature depends on the fact that you have quantum superpositions. If a thing can be over here, if it can be over here, then you have states where it's here and here at the same time. So this is a feature of quantum mechanics which is very central to the U stands for Schrödinger equation, if you like, or unitary evolution. What does the R stand for? Well, that's when you make a measurement. So I don't want to illustrate it with this slide too much, because let me do it in a more, I was invited to Odense in Denmark to give a lecture in honor of Hans Christian Andersen. It was to do with his 200th anniversary, and that was coming up in a couple of years, and so they invited me to give a talk. I began to wonder, why are they asking me? And then I remembered, of course, I've got this book, The Emperor's New Mind, which was, the title was based on the Emperor's New Clothes. And so I thought, well, I've got to better think of another story, so I thought of The Little Mermaid. And it related to quantum mechanics in various ways. The particular way it does in this picture, let me go to the next one. You see, she illustrates the quantum world, that's the fish and all that stuff, and the classical world is the bit at the top. And so you have classical physics, general relativity, and so forth, and Maxwell's equations to describe classical physics, and you've got quantum states and the unitary evolution, the Schrödinger's equation, that sort of stuff, where there's all sorts of entanglements and things like that, which are hard to believe and hard to understand, but nevertheless they're part of quantum mechanics. And what's the mermaid herself? Well, she represents the transition from one world to the other, and that is the reduction of the state, the thing I'm calling R, which is not part of current quantum mechanics. Current quantum mechanics makes a mess of it. There are all sorts of points of view, and some of them leads you into believing that all sorts of, if you have a thing which could be here and a thing could be here, and it's there at once, well, it's still there in the two places. I mean, Schrödinger illustrated this with his example of Schrödinger's cat, which was he put forward really to show the absurdity of his own equation, because his own equation would lead to a state in which the cat was alive and dead at the same time. Thank you. And he was just saying this is absurd. But nevertheless, that's what his equation leads to. But what you've got to do to make the cat either dead or alive, you've got to reduce the state. You've got to do what's called making a measurement. And what does that mean? Well, some people say it's a conscious being looking at the cat. I don't go along that route. What about the cat looking at itself and things like that? But I don't think it's anything to do with consciousness in that sense. But what I am trying to argue is that the notion of consciousness comes about through whatever is going on in the mermaid. So the mermaid is a mystery. It's not part of current quantum mechanics, but there's something missing. And this thing that's missing, the argument is, comes from bringing general relativity, and this is the illustration of the basic principle of equivalence. The top part of the picture illustrates, well, Galileo, let's pretend he actually dropped big rocks and little rocks from the Leaning Tower, and he's argued that they would fall together, and so an insect sitting on one of the rocks looking at the other, it would appear to that insect as though there's no gravity. So you can cancel out gravity by freely falling, and now we experience this now with the astronaut not feeling gravity even though the Earth is right there. So this is all part of Galileo's principle of equivalence, which is the basis of general relativity. And then here is an argument, I'm not going to go through the details, but it's an argument to show that the principle of equivalence, this is the Galileo-Einstein principle, is inconsistent with the principles of quantum mechanics, of quantum superposition. And you do two ways of looking at a quantum experiment done on a tabletop. Do you put the gravitational field in the normal way a quantum mechanic would do it, which put a term in the Hamiltonian, or you do Einstein's view, which means free fall, and then you see what the difference is, and the difference is something which relates to, at the bottom of the picture, you have a lump of material in two places at once, and this argument gives you an estimate of how long that superposition of that lump in two places should last. And this gives you a formula. Now this is a space-time picture of it. Now we have time going up the picture from bottom left to top right, and it's distorted by the presence of the lump. The lump is gradually put into two positions at once, and then it has to jump to one or the other after a time that you can estimate according to the theory, which is roughly speaking when the volume, the four-dimensional volume between the two leaves, one is the lump in one place, the other the lump in the other place, and it has to make a choice, and this estimates how long that superposition can last. And that's a formula that Stuart and I use. And this, we also say, is a moment of proto-consciousness. We only call it proto-consciousness because it has no sort of meaning or anything. It's the element, it's the building block out of which consciousness is constructed. So the idea is physics, but it's a physics that we don't yet know. And then Stuart got hold of me about microtubules. I'd never heard of them before. And so I realized that these were much more promising than just the transmission of nerve signals in our nerves. And then we come to this picture of all these microtubules together and all sorts of other structures involved. And this is more or less the kind of view that we have, but much more elaborated by Stuart and other people to develop this scheme of ORC-OR that we talk about these days. Thank you.
Thank you, Roger.
Okay.
You can switch the mic over. Why don't you?
Do we have? I'll sit here, I think.
Oh, actually, no, you don't have a mic.
I have this thing.
Is that right? Should I be taking this off?
All right, we'll have questions at the end. And it's my great pleasure to introduce the next speaker, who is a theoretical physicist from the University of Massachusetts and the founder of a field called quantum Bayesianism, Christopher Fuchs, who will speak on From Three Tenets of Cubism to a Whitehead-style creative pan-experientialism. Let's please welcome Chris Fuchs.
I've watched several Olympics, and you always see the kids who are coming out to compete holding up their phones and doing selfies. And it just dawned on me, I'm giving a talk right after Roger Penrose. I should take a picture of the audience, because it's going to be a tough act to follow. That's yours. And this? No. There we go. So I gave my talk a rather fancy title, From Three Tenets of Cubism to a Whitehead-style Pan-Creativism, but upon thinking about it, I decided that that's just too pompous. I should give it a more accurate title. The Day Cubism Shot Itself in the Foot. It'll pretty much amount to the same thing. What I'd like to do today is give you an introduction to a point of view about quantum mechanics, or you might call it an interpretation, that we call cubism, and see where that leads ultimately in an ontological direction. So cubism took its start. We had been talking about it since about 1993. My PhD advisor, Carlton Caves, his postdoc, Rudiger Schock, and myself. And after mumbling for a number of years, we finally published a paper in 2002, the paper that you see, where we try to take the point of view that probabilities in quantum theory can be understood from a Bayesian point of view. In other words, not as infinite relative frequencies, not as objective chances, not as propensities, but something more along the Bayesian lines of thought. That was 2002. Not many people paid attention, or when they did pay attention, they threw tomatoes at us. A real turn happened in 2012 through 2014 when David Mermin, who had been walking in the desert of quantum interpretations for much of his life, had an epiphany and said, "I believe cubism." And he started writing about it. When David Mermin writes about something, a lot of people in the Quantum Foundations community pay attention. So since 2012, 2014, cubism has been taken seriously as one of the better-known interpretations of quantum theory. Where does cubism take its start? Well, it takes its start in a point of view that the late E.T. Jaynes, Edwin Jaynes, had. Jaynes was a supporter or a propounder of Bayesian probability theory in physics. He used it mostly for statistical physics. Jaynes wrote, "Our present quantum mechanical formalism is a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelet that no one has seen how to unscramble. Yet we think that the unscrambling is a prerequisite for any further advance in physical theory. For if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we are talking about. It is just that simple. So there's a rather novel idea here that one doesn't find in most interpretations. You don't see it in the many worlds interpretation. You don't see it in the objective collapse interpretations. You don't see it in Bohmian theory, as far as I can tell. And it is that the theory is a combination of two things. It's a combination of subjective and objective, and they've been mixed together. And a good source of the confusion has been that they're mixed together. So the task at hand is to try to pull them apart and put the objective on one side and try to understand that as a statement of what reality is, or what the quantum world is. The starting point for Jaynes was that different people, that's not working. Maybe it's not on. Oh well, we do it this way. Different people have different knowledge. So there's a state of reality represented by the dot there. Wonder if the tech guys can give me something that works. Oh, here's the problem. There's a state of reality represented by the dot, whereas two different people might have two different probability distributions for where the dot actually is. Are they at fault? Well, no, not necessarily. They have different states of knowledge. This is where they get two distributions for a single reality. We were able to do some amount of work with that idea as breaking the theory into two pieces, but in the end it just didn't go far enough. And the problem was that the idea of knowledge, if you think of knowledge as true justified belief, has a factive nature to it. If you think of knowledge, knowledge itself is a kind of combination of subjective and objective. I say I know something, you prove me wrong, well, then I didn't actually know it. There are conditions in the world that can prove knowledge wrong. But the word belief is a looser fitting thing to the world. So we started to turn from Jaynes's version of objective Bayesian probability theory to a kind of probability theory that is known as personalist or subjective. And this then led to a lot of progress that I'll try to show you a little of, and it gives us a corrective to Jaynes's program. What we find in the end is that some, in fact most elements of the formalism of quantum theory are in fact personalist or subjective, more subjective than Jaynes himself would ever go. Whereas some relations in the formalism are objective as one could want of a physical theory. Notice the distinction. Elements in the theory are subjective, but some relations in the theory are objective. And in order to be able to suss that out, you have to make the distinction between subjective and objective to begin with. So you want to look for a statement about reality? Well then, what this tells you, this methodology tells you, is to look for the statement about reality not in things like quantum states, but rather in the relations that one finds within the theory. So now let me give you a sense of what I mean by truly subjective probability. This is an idea that goes back to Bruno Definetti, and here's the way Dennis Lindley put the whole topic. The topic studied is the situation of an individual who is faced with uncertainty about some events of concern to him. All of us find ourselves in this position. Whenever we cross the road, we are in a situation of uncertainty. We might or might not survive crossing the road. Definetti's task is first to recognize openly the uncertainty surrounding us and then see how we can best understand it, how we can best moderate the uncertainty in our lives. The main result is that uncertainty can only be described satisfactorily in terms of probability theory. The coherentist paradigm, this coherentist paradigm is egocentric. It is the tale of a single person contemplating the world and not wanting to be stupid. He realizes that to do this, his statements of uncertainties must satisfy the laws of probability. So the idea is there's a primitive notion, uncertainty, and when we formalize the notion of uncertainty, the best way to formalize it ends up with the calculus of probability theory. To make this concrete, let me give this kind of definition of probability. Probabilities, in this point of view, correspond to the value of lottery tickets. Consider the lottery ticket that's worth $1 if an event E occurs. When a bookie writes down numbers like P of E or P of not E, P of E or F, etc., what he is saying is, this is a price I am willing to buy or sell that lottery ticket for. I'll either buy it for that price or I'll sell it for that price. And this now is what we take as a definition of probability. But this has no mathematical structure, so the word probability is empty at this point. It's just the price of a lottery ticket. The way you get structure is by adding something that I'll call a normative rule. The normative rule says the bookie should never declare numbers that will lead to a sure loss in one trial. Not in the long run, but in one trial. It turns out that this one simple rule leads to all the laws of probability theory. So if a bookie has written down this price for a lottery ticket that is worth $1 if E or F occurs, and he's written down these numbers for lottery tickets about if E occurs, if F occurs, and he hasn't adjusted his pricing scheme so that the two numbers equal each other, then a gambler can walk up to the table and say, I will buy some of these tickets, and I will sell some of these tickets at your price. And if he's done that correctly, in one trial, the bookie will have a sure loss. Why do I call this normative? Well, normative implies that there's a should somewhere in this story. What should be? Well, it should be that the numbers that are written down for the lottery tickets satisfy this relation. It's not a trivial thing to write these relations. Generally, when one makes probability assignment, one gets one's information from different sources. So maybe the bookie has written down this number by thinking about one source of information. And he's written down this number from another, and this number from another. And if the numbers don't mesh according to this equation, he's done something stupid. Probability theory doesn't tell you which of these is the correct assignment and which of these are the incorrect assignment. It's just a normative guide. It says to the bookie, you've done something stupid, you better readjust your numbers. How does he readjust his numbers? Well, he thinks harder, or he gathers more data, or he looks at a larger variety of sources. From this point of view, what do we mean by probability 1? Well, it means that one will buy or sell a lottery ticket worth $1 for, in fact, $1, full stop. That's all probability 1 means. It means somebody is willing to pay a full dollar for a lottery ticket that's worth $1. Particularly, it does not imply the truth of the proposition. If I write P of E equals 1, it doesn't mean that E is true. It doesn't say that if E is a physical property, P of E equals 1 means that E has the objective value of true. Here's the way the subjectivist Richard Jeffrey put it. The Bayesian framework replaces affirmation and denial by a continuum of judgmental probabilities in the interval 0-1, endpoints included. Or what comes to the same thing, a continuum of judgmental odds in the interval 0 to infinity, endpoints included. Probability 1 corresponds to infinite odds. That's a reason for thinking in terms of odds, to remember how momentous it may be to assign probability 1 to a hypothesis. It means you would stake your all on it, but that doesn't mean it's true. Well, what does this have to do with physics in any shape or fashion? Well, let's think about the Einstein-Podolsky-Rosen criterion of reality. They say, of course, everyone probably in this audience knows they're thinking of a situation where they have two entangled particles, and Alice over here makes a measurement on one of them, and consequent to finding the outcome of her measurement, she's able to say what she would get at the other particle if she made the same measurement on it. So this is a situation that EPR were thinking, well, there's no superluminal signaling, so how can the particle on the right know that it should give the same answer as the particle on the left? So their criterion of reality was, if without in any way disturbing a system, one can gather the information required to predict with certainty, i.e. with probability equal to 1, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. The philosopher Tim Maudlin says of that statement, if I could make one change to the EPR paper in retrospect, it would be to alter the characterization of this criterion. The authors call it reasonable and in agreement with classical as well as quantum mechanical ideas of reality, but its status is actually much stronger than that. The criterion is, in the parlance of philosophers, analytic. That is, this criterion follows just from the very meanings of the words used in it. Now, Maudlin makes a big deal of that because then he says, this is the key thing that powers the following statement. What Bell proved and what theoretical physics has not yet properly absorbed is that the physical world is non-local. In other words, Einstein's wrong. There is spooky action at a distance, and it all hinges on this EPR criterion of reality. But most physicists are suspicious with this idea of non-locality because they ask, well, where does it stop? The experimentalist walks into his laboratory, he carefully calibrates his experiment, and he gets an outcome for a spin measurement. And those who believe in non-locality say, well, perhaps somebody sneezed in a faraway galaxy, and that's what led to your result. So physicists are suspicious of it. Cubists are suspicious of it. And in particular, we're suspicious of this idea that it is an analytic statement, the EPR criterion. Well, it's just not so in cubism because it uses a different vocabulary. Probability in cubism is of the subjective Bayesian variety, and it doesn't have the same meanings that Mr. Maudlin says would lead to an analytic statement of that variety. So for cubism, the great lesson of John Bell, there is a lesson in John Bell. It's not that nature is non-local, it's that nature is creative. Even when I make a probability 1 ascription, it doesn't imply the pre-existence of the value I'll find. It means I'm very confident of it. It takes the action of measurement to bring the actual outcome about. Quantum measurement represents those moments of a kind of creation that are enacted or noticed by a quantum measurer, an agent, a gambling agent. So more generally, let's think about quantum states. What do we do with quantum states? Well, we calculate probabilities from them. That's the ultimate use of a quantum state in any quantum mechanical calculation. But in the 70s, a new field arose called quantum information theory. And one thing we learned from quantum information theory is that if we consider a robust enough set of measurements, a set of measurements that are known as informationally complete, then the probabilities will uniquely specify a quantum state. So quantum states give rise to probabilities, but you could start the other way around and say probabilities give rise to this theoretical construction, quantum state. Well, if probabilities have to do with a tale of a single person not wanting to be stupid, then from this point of view, a quantum state is of the same character. Well, then, what about these quantum measuring devices or quantum preparation devices? Niels Bohr always drew them as big solid objects to represent the fact that they're sitting on the laboratory table and you can just look at them. Well, if you perform the same kind of analysis that you do with quantum states, use quantum information once more, then you can show that the specification of a measuring device corresponds to the specification of a set of conditional probabilities. And conditional probabilities being probabilities for a subjective Bayesian should be interpreted in the same way. So the description of a quantum measuring device, rather than being this solid kind of picture of a macroscopic entity, for cubism, these things are just as diaphanous as any probability assignment. They're not living on the table, they're living in an agent's thinking. This leads to tenet 1 of cubism. All probabilities, including all quantum probabilities, are so personal or subjective they never tell nature what to do. This includes probability 1 assignments. Thus, quantum states, measurement operators, and unitary time evolution operators have no ontic hold on the world. They all represent personal judgments. So in the Jaynesian split, here's what we've managed to do. We've managed to put the various pieces of mathematics, quantum states, the permission operators that describe measurements, unitary time evolution operators, on this side of a pile. They correspond to the subjective. Now, the question is, what's left on the right-hand side? And before I start to tell you what's left, let me just ask, could it get worse? And, well, it does get worse, or better, depending upon your point of view, if you consider the scenario of Wigner's friend. This is a photograph of Eugene Wigner, and his friend is behind him. That's Edward Teller. And you'll notice that Wigner has his back to Teller. If he wants to make the best predictions that he can about what he will see when he turns around, he'll use the calculus of quantum mechanics. He'll effectively put Wigner in a box and say, that's a physical system behind me. On the other hand, I think we've learned from Copernicus that we really shouldn't privilege one of these gentlemen over the other. Wigner, on the inside of his box, feels experiences. For instance, maybe he's contemplating this light switch and what it will do if he flicks it. Well, if he flicks it, then he'll either see a light come on or he won't. On the other hand, Wigner himself is using quantum theory to describe this, so he might be describing the whole situation unitarily. What gives? Is the Wigner point of view of getting outcomes correct, or is, the Wigner's friend point of view of getting his outcomes correct, or Wigner's where he uses the quantum mechanical formalism? Well, one can have one's cake and eat it too if you relativize the notion of a measurement outcome. This leads to tenet 2 of cubism. A quantum measurement is any action an agent takes upon the world, and its outcome just is the consequent personal experience this induces for the agent. Particularly, quantum measurement outcomes are not, to paraphrase Bohr, instances of irreversible amplification objectively recorded for everyone to see in advance, whose design is communicable in common language, suitably refined by the terminology of classical physics. This gives you a hint of why it's so difficult to read Bohr. So, Bohr had his heavy, solid measuring apparatuses. Quantum Bayesianism, cubism, has the experiences of the agent in their place. So this leads to this final picture, basically, of what cubism is about. It's about an agent immersed in the world and wanting to do his best not to be stupid with regard to how that world is structured. A measurement is, in this picture, an action that an agent takes on the external world. Taking the action on the external world leads to a consequent experience for the agent. The degrees of belief about what outcome he will get, what experience he will have, is summarized by this mathematical object. His degrees of belief about what he has done with these meters that are effectively part of his hand are characterized by these things, and unitary time evolutions also correspond to how he propagates one belief to another. When I first drew this diagram, one of my colleagues said it's like watching a quantum Bayesian shoot himself in the foot, because it seems to him that we've given up on all relation between quantum theory and reality. But notice that quantum theory can be used by anyone in this picture. I focused on one agent, but there are agents all over the world who are using quantum mechanics. Those other users for the agent in focus are just physical systems like anything else. And each of those individual agents are using the Born rule. So that tells you that the Born rule has an objective character to it. It's a feature of quantum theory that any agent can adopt. And just like in the general rules of probability theory, the rule is normative. And so when we wrote P of E or F equals P of E plus P of F, we thought of that in a normative sense. Now that we've recognized that quantum states and measurement operators are ascriptions of probability, then one can say, well, this says that the probabilities on the left must be adjusted to be in alignment with the various probability statements on the right. That's tenet 3 of cubism. The Born rule, the foundation of what quantum theory means for cubism, is a normative statement. It's an empirical addition to the coherentist paradigm, and consequently about the decision-making behavior any individual agent should strive for. It's not a descriptive law of nature in the usual sense, say the usual sense of general relativity, where a law of nature tells space-time exactly what to do. The Born rule is not like that. It doesn't tell nature what to do. It tells the agent how best to gamble. But we do want more reality. If you want more reality, then the question becomes, why this particular rule? Why this normative rule? What conditions of the world make this the right rule to use? And that's where the real work of cubism kicks in. This is a general lecture. If I told you about the details of cubism, I would bore you stiff because they become quite mathematical quite quickly. But what's at stake is trying to understand the Born rule as this normative rule in as clear and as possible. With the right kind of mathematics, again from quantum information theory, one can rewrite the Born rule to get rid of the mathematical objects of quantum states and measurement operators and end up with an expression that's purely about probabilities. Well, maybe you want more reality than that already. That's telling us something about reality, but what is it telling us? Here's what I think it is telling us. When we drew this diagram and said that quantum measurements represent those moments of creation that are enacted or noticed, notice that quantum states are not directly about the things that are happening in the world, and measurement operators are not about the things happening in the world, and so on. In this picture, the only thing happening is this little spark that flies between the external world and the internal world of the agent. Here's the way Wolfgang Pauli put it, and I have just a couple more slides. I'm more and more expecting a further revolutionizing of the basic concepts of physics in connection with this, particularly the manner in which the space-time continuum is currently introduced into it appears to me to be increasingly unsatisfactory. Something only really happens when an observation is being made. Between the observations, nothing at all happens. Only time has, in the interval, irreversibly progressed on the mathematical papers. This suggests, actually, that the notion of something happening, the little spark, is exactly what we would like to abstract. William James said it nicely. Here I take the bull by the horns and ask, why not? Our acts, our turning places, where we seem to make ourselves and grow, are the parts of the world closest to which we, are the parts of the world to which we are closest, the parts of which our knowledge is the most intimate and complete. Why should we not take them at their face value? Why may not the actual turning places and growing places, which they seem to be, of the world, why not the workshop of being where we catch fact in the making? Fact in the making is the key idea. This suggests that what cubism is aiming for is to abstract this little element that we find in the theory, always focused on the quantum measuring process, and say, this is what the world is made of. They're events of a sort, but ostensibly they all have a polarity, like Whitehead's throbs of experience. You look at the diagram, It's not immediately obvious, but it can be decomposed into an objective end and a subjective end. So I think Whitehead was onto something, and I think Cubism is a methodology for going in that direction. But Whitehead, per se, cannot be exactly right. Whitehead wasn't involved in modern physics, despite what some historians might think. His knowledge of quantum theory wasn't very deep. His vision, his ontology, was not tempered by the deep details of quantum theory. To ask why the Born rule is to construct a detailed picture of the characteristics of these actual occasions, in Whitehead's terminology, or throbs of experience. If we understand their characteristics, then we will understand why we should adopt the normative rule that we do, and you can reverse engineer. Why do we have the normative rule that we do? That tells us something about the characteristics of these events that are occurring in nature. But it's a long road. Cubism is a project, and there's still a lot of work to do. Thank you.
Thank you very much, Chris. Do you have your slides? We're good to go? All right, our final speaker of this session, and then we'll have a group panel discussion, is physicist Thomas Filk from University of Freiburg, who will speak on what is quantum-like in consciousness. Thomas Filk.
Yes, so do you have a microphone? Well, I love to walk around, but okay, so first of all, I should like to thank Harold and Stuart for inviting me and giving this talk. And maybe some remarks before I start. I will not talk really about the details of quantum theory, and I'm also not saying that consciousness is a quantum feature. What I want to do is to point out certain similarities, certain parallels in the phenomenon, or the phenomena which we observe in studies of consciousness on the one hand and in quantum theory on the other hand. Now, usually when I lecture on quantum theory, I start with a story which is reported by John Bell. Heisenberg and Dirac were somewhere in Ireland, and they saw a group of sheep, and Heisenberg was emphatic, it was cold, and he said, "Look, Dirac, those poor sheep have been shorn." And Dirac waited for a moment, thought for a moment, and then he said, "Yes, at least on this side." And this is a kind of warning that we shouldn't make statements about things which we don't observe, in particular when it comes to quantum theory, and I sometimes have the feeling also when it comes about consciousness. So in physics, then, this story might be told in the following way, that Heisenberg says, "Look, Dirac, all those dots, after all, electrons are particles," and Dirac might answer, "Yes, at least when we measure their position." So we cannot say anything about these when we do not make measurements. And I cannot resist to add a second story with a similar warning, being in the same session as Sir Roger Penrose. 2 years ago, I was walking in a small village in Switzerland, and I passed by a few houses who were in the shadow, and then suddenly a hotel or restaurant came up in the sun, and I saw this, and I was quite astonished to see that Roger Penrose has a hotel in this small village in southern Switzerland. But wait until you see the whole picture. So I think this is true also for quantum theory, and so these are the two warnings I give before I start. So this is a rough sketch of my talk. I will show a lot of similarities between phenomena in the study of consciousness on one hand and phenomena in physics on the other hand. Finally, I will make some remarks on what today is called quantum cognition and how they apply the quantum formalism in the context of cognitive phenomena. So when you see these pictures, and I think most of them have seen these pictures, you can see a rabbit or a duck on the left-hand side. You can see a young woman or an old woman on the right-hand side. Sometimes you see only one of them, but the rather philosophical question now I'd like to ask you is, what do these pictures represent when nobody looks? And you might say, well, the left-hand side, it represents a rabbit and a hare, or duck, a rabbit and a duck, or neither a rabbit nor a duck. You can say that presumably of any picture. I don't know, that becomes too philosophical for me. But the idea here is that sometimes, when you, in particular in these pictures, they're a good example that results are created by observation. And this is something which also Chris already referred to. It happens also in quantum theory. And it was by chance that I referred to the same physics philosopher as Chris did before, but that was a few years before he converted to Cubism. So David Mermin, he wrote an article in 1985, Is the Moon There When Nobody Looks? And he was referring to recent results on quantum phenomena. There had been a few experiments 2 or 3 years before which proved that at least on a level of elementary particles, indeed, sometimes certain properties are not there when you don't look. And maybe even the property of being a particle is not there when you don't look. That's what I said also in the beginning. So David Mermin cites another physicist, Pascal Jordan, who was one of the founders of quantum theory, saying observations not only disturb what has to be measured, they produce it. We compel the electron to assume a definite position. We ourselves produce the results of measurements. Now, this should not be confused with saying we produce the result. So we should be careful. What we do when we observe is we don't produce, for instance, a particular position of a particle. We produce the attribute of having a position. And so I think this is very similar to things which sometimes happens when you fill out a questionnaire and you are compelled to answer with yes or no, even though you feel that the actual answer is much, much more complicated and you are tempted to write a long article about the actual answer. So we compel a person to assume a definite opinion, and by the question, however, we do not produce a particular opinion, at least a good questionnaire shouldn't do that, but we produce the attribute of having an opinion about this question. And this is very, very similar to what happens in quantum theory, namely that by particular observations, we don't produce a particular result, but what we produce is the attribute of having the attribute corresponding to this observable. So this is a first similarity between a phenomenon in cognitive studies and a phenomenon in physics. Another one is the following, which for people working, for instance, in psychology or cognitive sciences or social sciences is very obvious, namely that when you make a measurement, it's a process which, first of all, is an interaction between an observing and an observed system. Second, it changes the observing system. Of course it does, because the observing system gets more information. But it also changes the observed system. And that was new in physics. I mean, when you go back to Newtonian physics, the success came from observing planets and predicting the trajectories of planets. And when you observe planets, you don't expect that you're observing these planets changes their trajectories. So for physics, this came more or less as a kind of shock at the beginning of the last century, that by making measurements, you change the system, you influence the system, something which is very well known, as I said, in the social sciences, cognitive sciences, and so on. So any measurement is an intervention, in a sense, which has an influence also on reality. And I use the word intervention here because maybe there are some people here working in psychotherapy, and there it is a technical term, and you can use it in that sense. Intervention, measurement is really an intervention, and when we call measurements sometimes observations, it's a very, I think, a bad expression which we use in physics. So one of the consequences, and I only mention this briefly here because I come back to these consequences at the end of my talk, is that order matters. So the results of measurements may depend on the order in which these measurements are performed. And what you see here is a very simple experiment which everyone can do who has either 3 sunglasses with polarized filters, or polarized glasses, I'm sorry, or if you use these old cameras which had polarizing filters. You put these 3 in a row, and depending on the order, there is no light going through, or there is light going through. So the first one is always in the same, it's always the same position. It's just to filter out a certain horizontal polarization. But then the second and the third one are interchanged here. And in the first situation, nothing would go through. In the second situation, some part of the light would go through. So order matters, and that is a clear signal that a measurement is not simply an objective observation, but it is a process which intervenes with the system. Another similarity, which is closely related to what I said before, the creation of results, is that I think in quantum theory, as well as in a science of or theory of consciousness, we deal with a kind of statu nascendi, so with a kind of coming into being of something. In Newtonian physics, in principle, we have Newtonian laws and we have initial conditions, and that settles it all. The whole history of this system which we are describing, maybe even of the whole universe, according to Newtonian physics, is fixed once we fix the initial conditions. And so there is no coming into being. There's nothing new entering here. But in quantum theory, it's different. So quantum states, also the states which Chris referred to before, they refer to kind of potentialities, even though he doesn't like that word, as far as he said in the beginning of his talk. These quantum states usually, in the usual interpretations at least, refer to potentialities. And the quantum rules, and one of the rules is Born's rule, which he mentioned, which gives you the probability that a certain potential event can become a real fact. These quantum rules refer how these potentialities become reality. And that is sometimes what some people call the collapse of the wave function. So you have a transition from potentialities to facts, and this transition is not deterministic. It cannot be predicted with probability 1. And again, I would argue that with conscious states of mind, it's very, very similar. They do not follow each other in a strict deterministic sequence of thoughts, but somehow, sometimes we have the feeling that ideas pop up or they crystallize somehow in our head, not according to any deterministic law which leads us from the beginning of our thinking to the end, or of our thoughts to the end. Another thing which is closely related to this is that it's almost impossible to keep quantum systems as well as consciousness, I think, completely isolated from the rest of the world for a long time. In quantum theory, people are trying to do that. It's one of the big issues in connection with so-called quantum computing. But the fact that we haven't made so much success during the recent years just shows us that it's very, very difficult to keep quantum systems away from an environment. And whenever they get in contact with an environment, they are influenced in this non-deterministic way. And with consciousness, I have the feeling at least it's the same. Even if we are in a dark room, even if there is no noise, it's very, very difficult to have consciousness completely isolated from a kind of environment, because even the itching of your hand or whatever, feeling something in your left leg or so, these are influences on consciousness which do not follow any deterministic law, do not allow to describe consciousness by some deterministic laws. Another catchword which became popular recently, also in physics, is contextuality. Now, contextuality, I think, is very well known in, again, study consciousness, study of cognitive systems, study of social systems. The context is very important. The way how I might answer a question depends on in which situation this question is asked to me, or may even depend on who is asking me this question, and so on. So the result of, also in physics, the result of measurements may depend on measurements performed simultaneously. Well, that alone might not have been a surprise in physics, but this can sometimes be over arbitrary large distances. And again, this is something which Chris referred to when he talked about the EPR paradox, or the EPR scenario. So it could be that, I mean, hypothetically at least, some measurement in the Andromeda Nebula has an immediate influence on another measurement which you perform here on Earth. And that now depends very much on which philosophy or which school you are from in the context of consciousness. At least I met some people working in the field of psychology who believe that similar effects are possible also with conscious systems. I don't know, but contextuality definitely is a phenomenon which is very common in conscious systems, but it is also there in physical systems, in quantum theory. Now this is maybe, again, a kind of catchword, free will. I wouldn't have used it if it weren't for this article by two mathematicians, John Conway and Simon Cochin. They both worked on the fundamentals of quantum theory. And this actually is the second article on this subject which they wrote in 2009. And they come to the conclusion, and they prove that really in mathematical terms, that if indeed we humans have free will, then elementary particles already have their own small share of this valuable commodity. Now, being mathematicians, they try to define what they are talking about. So they define what they mean by free will, and I leave it up to the philosophers to decide whether this is what free will really is. So they say more precisely, if the experimenter can freely choose the direction in which to orient his apparatus in a certain measurement, then the particle's response is not determined by the entire previous history of the universe. So that's their definition of free will, at least for the particle. At least, again, for physics, this came as a kind of, or this was a kind of shock when we realized, because it puts an end, in a way, to the principle of sufficient reason from Leibniz. So in physics, there are sometimes events happening where there is nothing, even afterwards, after the event has happened, there's nothing that we can tell why it happened this way and not the other way. At least if quantum theory is true. It always depends a little bit on the kind of interpretation which you favor. So again, I mean, you can say if you're a panpsychist, well, that's what I would expect. physicists are just investigating on a small scale what cognitive or conscious scientists are investigating on a large scale. But this statement is independent of whether you are a panpsychist or not. Okay, another similarity, the extension of the now. In Newtonian physics, we always thought that, well, time, at least along a single word line, that time is can be described by a real parameter. The now is a dot, and there then extension 0. And I mean, that was a problem for old philosophers, for Aristotle and others, that how dots, so combinations of now, can make up a duration, an extension. So in physics, in Newtonian physics, the now is still treated as a dot, if it is treated at all. But in conscious sciences, conscious experiences, we have something which is temporarily extended. It depends a little bit on the kind of processes, on the kind of authors you look at, but it's maybe something between a few hundred or maybe 100 milliseconds and 1 or 2 or maybe 3 seconds. These are different numbers, but it may also depend on the kind of process. Now, in quantum theory, it's similar, even along a single world line. There are processes which take a certain duration, and within this duration, you cannot tell causality or causal relationships. You cannot say if there are some events happening within this duration, which one was first, which one was second. There's a famous formulation of quantum processes in terms of sum over all possibilities. We have to sum all possibilities in order to get the total contribution. And if the probability, these possibilities also include interchanging orders, then we have to take both orders into account, and that means that in the end, this causal ordering is lost in these processes. So again, this extension of what now is, and for me now is a kind of transition period from these potentialities to facts. These transitions is not something which happens momentarily. There are other similarities which people sometimes quote. Entanglement is one of them. I will not go into the technical details. For me as a physicist, I'm always a little bit skeptical when people in the cognitive sciences talk about entanglement. But the idea here is that if on the left-hand side you recognize this as a beak, then presumably you would recognize this as a back neck. While if you recognize this as ears, you would say this is a kind of chin. So there's a correlation between what happens on this side and on that side, a strict correlation. And this is at least similar to some effects which you observe in the context of entanglement. Another similarity has already been mentioned, complementarity. Complementarity is an expression which I think became famous in the context of physics. Particle-wave duality or complementarity between a definite location and a definite momentum. And presumably, Niels Bohr got this expression, complementarity, from a psychologist, from William James. Actually, this complementarity is mentioned many times in the book of William James, but only one time in a context where it has a certain relationship to how complementarity is used today in physics. Another similarity dealing with uncertainty, and this is again something which refers to Chris' talk. So Schrödinger in 1935 called the quantum state a catalogue of expectations. And Bohr in the same year, he said that this quantum state is about what we can say about the results of future measurements. It's about prediction. So I think that comes already very, very close to this subjective interpretation, which Chris talked about, even though they didn't talk about Bayesian probabilities and so on. So for some physicists, quantum theory is just a very, very clever way of dealing with a certain type of information which refers to systems which do not behave in a deterministic way like Newtonian physics says. Now, I was quite astonished yesterday in some of the sessions which I attended that many people said that consciousness, the evolutionary advantage of consciousness might simply be that we can make better predictions from limited informations about an environment which does not always behave in a deterministic way. So that could also be a kind of similarity between what we do in quantum theory and what people do in conscious studies. For David Bohm, that's a completely different interpretation of quantum theory. The ontology is completely different from this subjective ontology which Chris talked about. There the electron is a real existing particle. But for David Bohm, the wave function carried the information for the electron, how to move. So essentially, this wave function contained information, and that is a similarity with the subjective interpretations. Now let me finally come to at the end of my talk, come to this subject of quantum cognition. It was initiated roughly 25 years ago by Dietrich Ertz in a few articles. And today there's a quite huge community. They have their own conferences each year working in this field of quantum cognition. Now the idea there is if there are these similarities between cognitive effects and between quantum physics, why don't we use the formalism of quantum physics and apply it to cognition? Whether there is quantum theory behind it or not is not the issue. Many people working in this field do not believe that consciousness or cognitive effects are quantum effects. But they believe that there is this similarity between these two fields. And as physics has worked out a mathematical formalism, which can be applied in order to make quantitative predictions, to predict numbers, so they started to apply this to cognitive effects. And I will give you just one example. It's an example of order effects, of what technically we sometimes call non-commutativity. And that is based on a poll which was taken in 1997. That was a few months before the Lewinsky affair became public. So that might explain some of the numbers which you will see. So there was a group of people, 2,000 people roughly. They were petitioned in two groups, each 1,000 people. And one group was asked the question, is Bill Clinton honest and trustworthy? And the other group was asked the question, is Al Gore honest and trustworthy? Now, these are roughly the results which this poll obtained. But then, because they wanted to study order effects, they asked the other question now to these groups. So the first group now was after they had been asked this first question and gave them their answer. They were asked the second question, is Al Gore honest and trustworthy? And respectively in the other group, the other way around. And these are the numbers which you finally got, or which they finally got. And I should say that these numbers are total probabilities in that group, so these four numbers add up to 1, while these percentages which I have given are relative to the answer they have given before, so it's always these two numbers which add up to 1, and same in the other group. So just if you want to analyze these numbers. But these numbers are not so very important. What is important is that it's obvious that there are order effects. Even yes, yes, going along this line doesn't give the same result as going along this line, or having yes here and then no would correspond to having no here first and yes then here. And in a group of total 2,000 people, the differences in these numbers are really significant. So there are obvious order effects, and the question is, how do they deal with these order effects? How do they describe them? So this is maybe the only slide which refers a little bit to the quantum formalism, and just take it as a cooking recipe. for me also the Copenhagen interpretation of quantum theory usually is just a cooking recipe. It gives me certain rules which I apply, and then I can calculate numbers. And then, on a completely different sheet, I have all these interpretations. So just take this as cooking recipes. And the cooking recipe is a possible state of mind, and this is a very simple system here, and that's why everything is drawn on a two-dimensional plane. A possible state of mind is represented by an arrow, and the arrow has a definite length, let's say length 1. And so you have different states of minds in which people can be in. The black one corresponds to a kind of average state of mind of a person who has not been asked the question yet, any of these two questions. The green one here, G go true, means that this is the state of mind of people who have answered the question, is Al Gore honest and trustworthy, and who said yes. The other one, orthogonal to it, is those people, the state of mind of those, represents the state of mind of those people who answered with no. And the same with Clinton. And the angles, the relations between these arrows, which I've shown here, just come from the numbers here in the first line. None of these numbers down here have entered. So just the numbers in the first question, where there's no order effect yet involved, enter in the way how these arrows have been drawn. And the only thing I wanted to show you is, why does quantum theory predict that there might be an order effect? So what you do is, when you make a kind of measurement, so when you ask the question and you get an answer, what you do is you project the state of mind in which you are in onto the new state of mind in which you are in after you gave the answer. And then if you ask the second question, so this one here is Gore first and then Clinton, you end up with this one. And this is an arrow which is still quite long. It's a little bit shorter than the original one and indicates a quite high probability that this is going to happen. While if you do it in the reversed order means you first project onto Clinton. That's the question which now is asked first. And then you project onto Gore. Then you get an arrow which is much shorter than the one we've seen before, which indicates that the probability that this process will happen is a different one than the other, the reversed one. So that shows clearly non-commutativity in this calculus, and this is how it is applied in quantum cognition. And that brings me more or less to the end, just one concluding remark. In physics, we very often define objects like photons or electrons or elementary particles, or attributes like charge or mass or energy and so on, by the way we can measure these quantities, or these attributes. So we take the experimental signature as a kind of definition for this object or this attribute. We have no idea what these objects or attributes are in reality. We have no idea what charge is, we have no idea what mass is, but we know how to measure them. And this refers a little bit to the talks we heard this morning, that maybe we shouldn't look for definitions first. What is a conscious system? What is a self-conscious system? What is a cognitive system? But just define these concepts in terms of experimental signatures. And that, I think, was also a suggestion given by the speakers this morning. And this brings me to the end. Thank you very much for your attention.
Thank you, Thomas. Chris, where's Chris? You want to come up and have a seat? And I'll let you guys share this one. Okay.
Oh gosh.
You get two among three.
Oh gosh.
Did you take one of the
I've
microphones?
got
You have.
Oh, he's got, okay, great. Thanks to all three speakers for very interesting talks. And we have time for questions. Don't be shy.
tend to be on a one-track mind, but Professor Filk, the extended now, there's the measurement of the extended now, which milliseconds, you said, but then there's the measurer. The measurer, the one who's doing the measurement. Now, isn't the extended now predicated on the now of the measurer, which can't be measured? It's a predication that there is somebody in some kind of an immediate state that's measuring a now that can be measured. So aren't there at least two nows?
Yeah. Let's see. Does that work? Oh, yes. Of course, when I say there's an extended now, and then I quote a number like 500 milliseconds, then you can ask the question, well, obviously this system itself could not measure these 500 milliseconds. So in physics, of course, what you do is then you compare with a system which is not considered, at least on this level, as behaving as a quantum system. So we have clocks which can be very accurate, which can be accurate, let's say, to the 10 to the minus 9 or 10 to the minus 10 seconds, or even more accurate. And then we use this external clock to compare with the process which happens in a quantum system. And in these quantum systems, you can in principle have nows which are extended with respect to our clocks for almost an infinity. Billions of years. Nice examples from John Wheeler, who had these billions of years delayed choice experiments. So in these systems, within the system, you do not have a clock which can measure any sequence. That's more or less the statement. Outside, when you compare, then yes, you have.
But isn't there still the predication that some measurement of some kind of the duration, you use the word duration, is based on something that is happening in the experimenter's state, which, in other words, one is predicated on the now of the experimenter? Somebody is doing the observation. Isn't there...
Yes, but it's not this somebody who measures this time in his or her consciousness, but he or she uses a device, and she just reads off the device. And that is accurate to, let's say, 10 to the minus 9 seconds or so. So I wouldn't go that far.
Okay, thanks.
Do you want to comment?
I'm very confused by this. Well, this is supposed to work. That's why. Does it work? Okay. No, I'm very confused by all this because my understanding of quantum mechanics is that there is a well-defined now, a universal clock. It's just like in Newtonian theory, and there's no uncertainty or anything about it. You can make measurements, and sure, but there's a Schrödinger equation just ticks away according to a universal clock. Of course, if you bring relativity into the picture, then that's a different story. But quantum mechanics, the state just... I don't quite understand the issue that's being... I don't understand your point of view, but that's certainly not my point of view.
Maybe I should clarify. What I mean is that during these processes, there is no internal clock which measures it. As you said, you might have always this universal clock in the background with respect to which you can measure events, and then you can say it happened at this and that time. But we know that within the system, in order to define a clock, for instance, you cannot take an eigenstate of the Hamiltonian because they don't experience any duration. They are static. They don't change. So for me, a clock should be part of the system. So let's say my definition of time here is more related to what Einstein said when he said time is what you measure on the clock. So the problem is, what are the clocks which I use in order to measure duration or time? And if I'm requiring that a clock is part of the system, so within the quantum system, then these processes have a duration in which, let's say, causal ordering, one before the other, is not defined.
Well, that's a different view from what I have. I don't...
Back
I
there?
mean, there are lots of other uncertainties in quantum mechanics, but I didn't think time was one of them. In standard quantum mechanics, not quantum field theory, not relativity, that's another issue. I mean, time just ticks away, and you have a state which... I mean, you're talking about internal clocks or something, but I'm not sure what they are. The theory, there's an absolute notion of time, which is external, if you like, but you may measure that or you may not. Anyway, sorry, I shouldn't. I should leave it to somebody else.
Thanks. A question for Dr. Fuchs. You appear to be defining your physics in terms of experience, which seems a very satisfactory way of doing things. Would it be fair to say that a physical event is of a type that can belong to a chain of similar events of a similar type, which if you put a human being, which is another cluster of physical events, in the right place, in the right context, you can predict a certain experience, which would suggest that the philosophical zombie is a contradiction because it's not physical.
I'm not completely sure I understood what you were saying, but let me outline something that might be relevant to what you're asking. So in the philosophy of William James, he tried to construct, or he has two very late papers, one of them titled Consciousness Does Not Exist, and one of them titled A World of Pure Experience. And he posits that the stuff of the world is what he called experience. And he went to pains to explain that experience was neither material nor mental, but when put in association with other experiences, would take on the one characteristic, mental, say, or the other characteristic, material, and perhaps any number of other attributes in between and in other dimensions as well. So I think the thing that Cubism is pointing to is that these happenings that are the outcomes of quantum measurements are of this kind of character. They're neither mental nor they're physical. When one thinks in the context of quantum theory, one clearly has an observer on one side of the story and an external physical system on the other. But the idea is to abstract those two poles away and be left with the event itself. And along the lines of James, I think that it's neither material nor mental, but that does not make it beyond the reach of physics. The reach of physics comes in when we write down equations that say how best to gamble in light of a world of this character.
Yeah, I would agree with that. That wasn't really my point, but it's just a technical thing as to whether a philosophical zombie is actually a contradiction in terms, but never mind.
Well, maybe try to explain it to me later when I have more time to think on what you're... Now you can't be heard.
Okay, later.
Yes, my question to Thomas about the last, part of conclusions. So, about your idea to relax with definitions, it looks like the definition will define the theory the same way as contextuality you described. So, isn't it just an attempt to escape the responsibility of observer to stop to define clearly? Because you understand that definition will really define what will happen afterwards.
Yeah, well, my point was that we cannot define the concept of charge without referring to how we measure it. So if you're looking for what is the ontology of what is reality here, what is charge in reality, I must say I don't know what it is. I know how it interacts, how systems which are charged interact with other. I know what to observe when an object is charged. So I define charge by a certain measurement procedure. And even though I don't know what it is as in any ontology. I can make myself an ontology, but that's irrelevant. And so I think this happens very often in physics. I was quite astonished, at least when I thought about it, that even such common concepts like energy or so, actually, I mean, there are mathematical definitions, but they depend on the model which you use. But in a particular measurement, of course, it's also the model which tells you, in principle, what do you measure. But, I mean, I define then a certain quantity by the reaction or the experimental signature which I see. I mean, that's how the elementary particles are measured, let's say, at CERN or so. They measure certain properties by using certain devices, and then they define, okay, now we have observed an electron, now we have observed a positron, and so on. But what an electron is, let's say in any philosophical sense or so, I must say I don't know. I don't know whether that answers.
But when you measure, you measure according some definitions anyway. You can't escape definitions fully.
I need these definitions, otherwise I cannot come up with a theory which produces numbers in the end. And that's the advantage, that the theory doesn't depend on me knowing exactly what the ontology or so of charge is. For the theory, it's sufficient to know how charge is measured.
My question, if you will say that the theory and result of measurement is dependent definition, maybe it will be like more clear and not
well, of course, I mean,
definitions.
if I make different definitions, then in the same experiment, I can say I observe different quantities. We have examples of this where, let's say, we observe something, we measure certain quantities, and now it depends on the theory whether, for instance, I have measured a force or whether I have measured the curvature of the universe.
In the back.
Hi there. I'd like you to explain the observer thing to me. So, as an example, with deep field view of the universe, do you guys believe that when the light goes into Hubble telescope and then a conscious human looks at that photo, that the galaxies 10 billion light years away somehow collapsed and came into existence through the active observation that has happened in a laboratory on Earth? Or do you believe that the whole universe is actually out there, or it actually does require an observer to view it, to collapse a wave function and create existence? I find it a really strange concept.
Who were you addressing with your question?
Oh, so just a general question, so just general quantum question.
I'll take my shot. I didn't much understand what you were saying. I had trouble with your accents. I apologize.
Sorry.
Well, I think you were asking, does the active observation create faraway galaxies?
Yeah.
And of course, that perhaps depends upon your interpretation of quantum mechanics. I can speak for myself in saying that I well believe that there is stuff going on behind the moon. I believe there is stuff happening far away. There were things happening 13 billion years ago. Things were happening all the time. Then, in my own point of view, in the point of view of cubism, is to say things were happening. Things are happening all around us all the time. But quantum mechanics isn't directly about that. Quantum mechanics instead is how I can best survive in a world where things are happening in certain ways. So by this light, what about the wave function at the beginning of the universe? Well, there was no wave function. A wave function is not a real thing in this point of view. Things were happening, but there were no wave functions. Things were happening in 1924 here on Earth, but there were no wave functions. It was only when we had a good idea for how to better handle our physical experiments in early 1926 that wave functions came into existence. So from this point of view, it's not about faraway galaxies coming into existence, but when do wave functions come into existence?
Okay.
And I would say wave functions don't come into existence until there's somebody using them.
Okay, so you do believe in independent external reality?
No, I keep independent external reality. It's not identified with wave functions.
Okay.
Wave functions are to do with a calculus for making decisions. One needs a decision maker. One needs some entity that is sufficiently educated to use the methods of quantum mechanics.
But is
But the
that-
world is still there.
Yeah, okay, yeah. So, but you guys don't believe in like a universal observer. If you have a premise of an observer, it seems to me, if everything has to be observed to exist, the only way that can be is if there's a universal observer. It seems like you're believing God, basically. It seems like a absolutely illogical premise.
Thomas will answer why that's
So-
wrong.
Yeah, I don't believe that. But
Why should I? I mean, I have the same problem with you. I'm sorry. No, maybe commenting more on what Chris said. In my language, I would say interactions have always been, since the beginning of the universe, systems have interacted, and this interaction determined to a certain degree then what happens. And what in quantum theory is so special that I, as an experimentalist maybe, I make a decision what kind of experiment to make. So I make a decision whether I make this interaction with the quantum system or whether I make a different interaction with the quantum system. And this decision has an influence on what happens then. And I think this is not something special. What is special is that when I make a decision and say, okay, I put my polarizing beam splitter or whatever here in this position, that then something comes out which was not determined in the sense of elements of physical reality, which Chris mentioned. There was no element of physical reality which determined whether the photon will go left or right. But it's my decision to make observations which influence the reality. And I think from a social point of view, again, I would argue that's the same in psychology, that's the same in social sciences. When a psychotherapist makes a decision to ask a certain question to his or her patient, that has a big influence maybe on the way how the rest of the therapy works. So that is not something that we can say. I wouldn't say that implies there were no galaxies before there was humanity.
So is it right to think quantum theory is the interaction of consciousness with independent external reality?
That depends a little bit on your interpretation. There are people who would say yes, I don't say no.
Right, okay.
I do say no.
Thank you.
Roger, do you want to comment?
Yeah, I guess my point of view with regard to quantum mechanics seems to be very different from that of my fellow panelists here. I mean, it seems to be conveyed as some kind of rather wishy-washy thing, which depending on the observers and things like that. Whereas the view I have of quantum mechanics is a very precise theory, and it has to be. We know it's very precise, which describes how the state evolves. So if you like, the Schrödinger equation. And it's very precise. The only trouble is that when you have some kind of object which is too macroscopic in some sense, then it seems to not follow this equation. And that's what's called the collapse of the wave function. So you have the wave function evolves very precisely according to Schrödinger's equation. But then you bring in something which is called a measuring device. And then, for some reason, that's big enough that it doesn't actually... You see, in the Schrödinger equation, you have particles in lots of places at the same time, and that's what happens. The quantum state describes what's called an amplitude for it to be in each place. It's not a probability. That's something which I worried about in your description, that you could apparently talk about the different probabilities. It's more than that. It's probabilities, and there's what's called a phase as well. So you have to know that phase as well, and this is what you call an amplitude. So it's not just that the thing is here with a certain probability or here with a certain probability. It's got to have that phase as well. Okay, if you have all that, that's the state, according to the Schrödinger equation. But the trouble is, when you get some things which are too big, in certain sense, it doesn't seem to follow this equation, and you get a jump from one state to another. And that was always a great puzzle to Schrödinger. He was very puzzled by this, because the physical state does not seem to evolve according to that very precise equation. But I mean, there are ways of measuring the quantum state and get very precise agreement with the Schrödinger equation. There's no question about it. It's not a wishy-washy theory in some sense, in terms of everything is just probabilistically defined or something. It's very clear. The only thing which is not clear is where the theory seems to undergo these jumps. And that's when you make a measurement. And in the view I hold, which is the sort of thing I was very partially describing here, is that there is something else which comes in, and that comes in when you have too much mass displacement. And instead of remaining in a superposition of these two locations, it jumps to being one or the other. And that's what seems to happen in the world. And people will worry about that because they think, oh, that must be very subjective or something. Well, that's one view. But my own view is it's a very objective thing, but it just doesn't follow the Schrödinger equation. But if one talks about observers and what people think and measurements in terms of, I don't know, I just feel the theory gets too wishy-washy, and you don't see the huge precision that's there in the theory. It's very, very precise. As long as one's talking about displacements which just don't get too big, and then you find the system flops into one or the other, which is this very mysterious collapse of the wave function, which needs a theory which we don't have as yet. But this, if you're looking at a small enough level, particles or whatever it is, then you don't have any problem with this. And there's no wishy-washiness about the time or about what the state is and how it evolves. It's very clear. It's just that when it gets too big and the superpositions get too big, and then you seem to have to jump from one state to another. And that's what's involved in making a measurement. You somehow magnify up these small quantum things up to a classical level, and then you have to make turns into probabilities. But at the quantum level, there aren't any probabilities. It all just follows this equation.
If I can give I'll try a brief response to Roger's choice of the word wishy-washy.
Sorry.
I like to give the example of, and sometimes in lectures, I walk into the lecture hall with a copy of Leonard J. Savage's book, The Foundations of Statistics. In this book, Savage gives a derivation of the rules of probability theory and of utility theory. He starts with a set of axioms, and then he fills in all of the various things he needs, and then he gives a derivation that the maximizing expected utility is the best way to proceed about your business. There's certainly nothing wishy-washy about developing decision theory from a number of precise axioms. Now, if you look into the same book and ask of this book, this user's manual, how do you define, if you look into the book and say, well, where's the chapter that defines exactly what it takes to be a user of decision theory, you won't find an answer. So similarly, I think of quantum theory in this way that I do. It is an addition to decision theory. And just as you can't look into a book on decision theory and find a precise definition of what it takes to be a user of decision theory, you're not going to be able to look within quantum theory and find a precise definition of what it takes to be a user of quantum theory. So at least from that perspective, I would say there's no wishy-washiness about this point of view, none that one wouldn't find in any development of decision theory. What it takes is for one to say, I'm going to stop thinking of physics as a direct description of what is exactly in the world, and instead take the point of view that quantum physics, at least, maybe not all of physics, but quantum physics is not a direct description of what's happening in the world, but a system for making better decisions in light of the world that you're in.
But I still worry about your comment about the probabilities defining the state. I mean, you need to know the amplitudes.
Yes.
In the phases,
Actually,
yes.
this is very good. The last time we spoke, I think, was in 2012, and I posed a mathematical problem to you. You can find a formalism that is isomorphic to quantum theory that uses no complex numbers, only uses probability calculus. That depends upon a very special, you can do it. You can just do it. You can also make it pretty if a certain mathematical structure exists. And that's where I consulted with you. We'll talk about this later.
Yeah, perhaps we should leave it at this point. Yeah.
Over here, please.
Thank you. I'd like to delve further into the nature of these probabilities as statements of belief. So we know that if probabilities are a statement of what I believe to be possible and how likely, and when it comes to collapsing the wave function, one of those possibilities is chosen to be reality by something we might call proto-consciousness, then shouldn't I take the life advice that if I really believe, I put all my stake on jumping off a cliff and flying, that will be the one that happens? Or is there a different source of probability that is other than my belief?
I certainly don't follow that. I mean, it's not saying that it's... I simply don't follow the argument there. Why do you, if you believe you can fly, it doesn't make you able to fly? The belief is not the probability. I mean, that's a subjective. You might be completely wrong. You find you can't fly, so sorry, that was the wrong probability. But I don't quite see what that's got to do with quantum mechanics.
What would be the right probability then?
I'm sorry, did I misunderstand? Yeah. I mean, the probability there is a very subjective one. It's an opinion of what the likelihood is of something happening. Whereas quantum mechanics comes up with these very precise numbers. It doesn't tell you which of the alternative. When the state collapses, it might collapse this way or that way, and the probability is given as to whether how much more likely is that than that. That probability is defined by the theory, but that's the part which talks about the collapse. Now, there's no subjectiveness in that. It's just it's an inbuilt probability according to the theory. It's not anybody's opinion. And you can do measurements. You can set up the same experiment many, many times, and you get out the probability, agree exactly with what quantum mechanics predicts. So I don't understand why it's got anything to do with the belief. Perhaps that's not what you're saying. Perhaps I misunderstood you.
That's the left side, from my point of view, the left side interpretation of this stage. The right side interpretation of this stage would say something like the following. If you start with a prior probability for probability of some hypothesis, and you also have a probability for the hypothesis given some data, a probability for a hypothesis and some data, then upon gathering some data, one would use Bayes' rule to update from the prior to the posterior. The posterior is completely determined by the conjunction of the prior and the data. So there's nothing imprecise about what one goes to at the next step, given what one had at the previous step. So the point of view on the right side here, your left side, is that a quantum state, so when Roger says these are very precise probabilities, I would say, well, a quantum state plays the role of a prior probability. And then the rules for updating quantum states is just like Bayes' rule. So given the prior and the data, one updates to a perfectly precise new quantum state. There's no wishy-washiness in that again. Now, actually, this is interesting. I don't know if you find it interesting, but in my early life, I started out as a Roger Penrosian. I had read The Emperor's New Mind, and I was blown away by it. And especially the idea that there were two kinds of evolution. There was U and R, and U was law-like, and R had a kind of element of freedom or randomness or free will or what have you. but it was based on making sense of the idea of objective chance. So when one specifies a quantum state and one specifies a measurement operator, there's no wiggle room. You can calculate a probability for the outcome of a measurement. And I thought, this is great. Now I've got to understand these objective chances. And I started exploring the path along frequentism, and that was full of contradictions. And then I started exploring the path of propensities, and I found that the extent to which one could make sense of propensities, one always relied on frequentism, and that was contradictory. So it was only after a long, long process that I came to the, I don't know if maybe Professor Penrose will say I gave up, but I gave up on objective chances and realized that the more sensible notion was the subjective notion, and that in fact, after quite a number of years, came to the appreciation that when one says the quantum in a textbook, assume the quantum state is this and the measurement operator is that, it's nothing more firm than in a statistics book where the problem says, suppose the prior is this and this kind of data is gathered, calculate the posterior.
All right, we have, looks like 7 questioners and just a couple minutes. Maybe we'll go a little extra, but please be brief, both the questioners and the panelists. Back there.
Thank you. I have a question to Dr. Fuchs. I think so 30 years ago, I had long discussions with Carl Friedrich von Weizsäcker about Definiti's conception of probability. So I want to ask you, also in the light of the lecture of Professor Firk, where are you the real differences between your concept and the normal Copenhagen interpretation? Thank you.
So for me, in brief, in the usual Copenhagen interpretation, at least as a Weizsäcker, he would view the probabilities that one uses in physics in an objective way. There is a right probability assignment, and there are many wrong probability assignments. The point of view of Definetti is, before the event, before a measurement occurs, there is no such thing as a right probability. And this goes so far as to say probability 1 is not right. Probability being right or wrong is something that is declared, only in some cases after the fact, but never before the fact, and that's the key distinction.
Yes, Chris, I would like to start with your Whitehead quote you gave about the throbs of existence.
You used it in your talk yesterday.
Yes, but Whitehead says drops of existence, and I think that's a very big difference because Whitehead is known for his knowledge of literature. He uses his words very well. Talking about drops of existence, of course, implies that there is sort of an isolated entity from something, from a context. And I bring this in context with sort of this status which is given to the subject. Of course, coming from the humanities, I find it great that the subject finds entrance into physics, but this image of the subject as something like a closed entity who decides on his or herself what to do, of course, that's an image of the subject which goes back to Enlightenment and which in philosophy, in the humanities and cultural studies, in sociology, you will not find it anymore there.
Correct.
So my question would be, do you need this concept, which is sort of far behind what's going on in other disciplines for the sort of plausibility of the formula, or why do you use this concept?
So I would say that every cartoon I draw is provisional. It's a project. And for instance, I'm quite attracted, I wish I could repeat the quote for you, but there's somewhere in James's 1895 or 1890 psychology book where he says, I define the self in the widest possible sense. A man is not only his physical body and his thoughts, but also his clothes and his wallet and his wife and his children, his yacht, and his lands, I believe. So cartoon that you saw of this isolated entity called the agent or the self, I think is just a provisional kind of move. Where it will go in the end, I don't know. But just a brief note, I have seen throbs of experience, and I think I'm relatively scholarly. I've also seen drops of experience. So I'll make a bet with you, and maybe I'll lose it. But I would bet that we can find both phrases in the corpus of Whitehead.
Okay.
And we'll find at least one of them, and we might find both.
Okay, I quoted it.
And if I lose, I buy you a beer.
Oh, I copied it from Process and Reality. So at least there's one version where he says drops of experience. Okay, thank you.
Thank you. In the back, that'll be the last question in the back.
Okay, this question is for all the panel. If one believes that consciousness is fundamentally going to be explained in purely physical terms, then obviously quantum mechanics, given the nature of quantum mechanics, describing the world in microscopic level, clearly must underpin consciousness in some way. But how does one make the leap from the microscopic quantum level to the more brain scale consciousness level? How does one make that kind of conceptual leap?
Well, the view that I hold on this is that consciousness is not to do with the quantum level. And this is the view that Stuart and I have tried to develop. It has to do with how when things get too big. You see, the quantum level, if you're talking about individual particles or small quantum systems, small systems, physical systems, small in the sense of not very much mass, then they behave extremely precisely according to quantum mechanics, let's say the Schrödinger equation. It's extremely precise. The only trouble is that when you get big enough, that it's what's called making a measurement, but making a measurement involves wheeling in some piece of apparatus which is much larger than the stuff you're measuring. And so you have to consider the whole system, which includes the piece of apparatus. And then you find that you are driven to these probabilities, and it's not just following the Schrödinger equation. So the U that I described in my talk was following the Schrödinger equation. And that works beautifully as long as you don't have huge displacements of mass. And what huge means is not very big from our perspective, it's very big from the quantum particles perspective. Now then the argument is that at that level, when you start having two large masses being displaced, it does not follow the Schrödinger equation, but it does what people use when they make measurements, which is the R process in what I was describing. And that's when the wave function gets collapsed. And yeah, it's a huge puzzle. Quantum mechanics works beautifully well with seemingly no corrections needed and with extraordinary precision, as long as you're talking about displacements of things which don't come to too big a level. So the idea here in the scheme that Stuart and I follow is that in microtubules, you have not just in a single one, that's not enough. That's too small a level. You don't get the reduction of the state with single ones. But if you've got lots of these things acting in some kind of concert over large areas of the brain, well, they do get to the level where the mass displacement becomes significant. And then you've got to worry about the collapse to one state or another. Now, it's in that collapse that the element of proto-consciousness comes in. It's not prior to that. It's not at the quantum level. And it's not when you've got things behaving essentially classically at that level. It's at the borderline between the two. So if you like, in my picture of the mermaid, it is the mermaid. It's not the sea underneath. It's not the scenery above. It's the connection between the two. It's how the quantum world emerges into the classical world. And that requires something that we don't have in quantum mechanics, a proper theory which describes the collapse of the quantum state. And the argument that we're making is that the element of proto-consciousness comes about exactly at that moment when one has to collapse the wave function. It is the collapse of the wave function. And that collapse can involve quite a large area of the brain. It doesn't have to be localized, and it's not likely to be localized in a single microtubule. That's much too small. You need to have lots of them. And they could be spread over big regions. So that's the perspective that we have.
Yeah. Billions of tubulons, nanograms of protein, I think. Very briefly, we're over time, just 30 seconds each, and see if we can finish this up, please.
I'm a neurosurgeon, and I have real difficulty in understanding the quantum mechanics. I would like to go some basics, and I would like to take your definitions on consciousness and mind in the most simplest terms. But the main requirement of mine is I need some help to understand. Every day I'm making operations and I am changing to human brains, and I'm asking myself if this human brain is creating consciousness or this brain is created by consciousness. I would like to take your opinion on these definitions.
I'm not quite sure I see the point of view I'm holding with Stuart is that consciousness arises in this physical process which is outside our current understanding of quantum mechanics. This is the collapse. What is it that causes the quantum state to collapse? And that is something happening within our brain. It's not, do you say the brain is causing it, or do you say it's causing the brain? It's what happens, and I don't like to say one is causing the other. I mean, it's part of the brain. It's the brain's action which depends upon these processes, and that's, I don't like thinking of it in terms of somehow something external to the brain or something. It's within the brain. It's part of the activity of the brain according to the theory which goes beyond current quantum mechanics and which encompasses the collapse of the quantum state as part of this extended theory. We don't have that theory as yet. I personally, the view that we hold is that this happens because of a conflict between Einstein's general theory of relativity and quantum mechanics. And you start to see a real tension between these two theories, and you can see that already. That's not controversial. That tension is something which can be resolved by the collapse. How that happens is not yet understood, but at least that tension is there. And to say that it's the brain causing it, well, it's part of the brain's action. I'm not quite sure how you say that. If you include what the microtubules do, okay, then but then it's the consciousness comes about as part of that process.
So may I just quickly comment that I think that there's a certain very vague similarity between the left-hand interpretation and the right-hand interpretation on this count.
I keep worrying about which is left and which is right, because the audience...
You're to my left.
On the audience, I'm on the right-hand side.
And I'm on the right, and of course Thomas is stuck in the middle. But
Okay.
This relates to the previous question and this one. From the point of view over here, consciousness is associated usually with something that uses quantum theory. I'm thinking of quantum theory as an instance of decision theory. And just as you cannot derive the notion of the user of decision theory, suppose it's conscious, you're not going to derive that from decision theory itself. You're not going to derive consciousness from quantum theory in my point of view either. So you won't derive consciousness in quantum theory. You need consciousness to cause collapse.
No,
I
we don't
think
need that.
yes, no.
That's Copenhagen.
That's not our view, I think. Yeah.
That's not our view.
Yeah.
Well,
Collapse causes
you're
consciousness.
proto-consciousness. You're proto-conscious.
That's happening everywhere. We don't need consciousness to cause that.
Okay, well, I've also got things happening everywhere. But I would have said it like this, that I can't look at the formalism of quantum theory on this point of view. Forget the similarities, maybe there are none. I can't get it from quantum theory because it presupposes the user of quantum theory.
Yeah, we certainly agree that current quantum theory does not encompass consciousness. I mean, that's what we're saying. We have to go beyond current.
So there is that much similarity then. We do agree on
Yes,
that.
okay, yes.
I would just tell my neurosurgeon colleague, take care of your patient's microtubules and talk to your anesthesiologist. Real briefly, two more, and let's wrap it up.
I'll try to be quick. A question for Roger. I wonder how understanding does not need further validation. You know, I got the chess piece. It award my biology. I felt it. Okay, I get it. It's a draw. But how so? This does not further validation, understanding as a whole, because maybe somebody cannot understand it, and what is the mechanism for not understanding versus understanding? Is really health of microtubules or what else? So if you can expand a bit in short about understanding and to what is referred to.
But the question is, how does understanding come about from these elementary proto-conscious events? Well, it needs a theory. We see, it's what I'm saying is somewhat negative. The statement is that understanding, as far as I can see, and I think the arguments are strong, that understanding does something which is not following a computation, and that there is something deeper which gives us a selective advantage over creatures which perhaps have somewhat less understanding, and that understanding is a feature which allows us, I mean, the proto-conscious elements have to be somehow, I mean, that's what the orc part of orc-OR is. It's got to be orchestrated. It can't be just an individual event which has no meaning to it. It could go one way or the other, and it's just a probability. But if it's part of a bigger system, like the orchestra I think Stuart talks about, and you've got much bigger structure which fits in terms. I mean, it's not a random process, is the idea. There's something deeper. I mean, quantum mechanics just gives you a probability. So the argument is it's not exact. It looks like a probability in isolation, but when it's combined with other things, it's something which behaves in a way which is not simply random and which has some content to it, which involves whatever understanding is. Now, I don't know what understanding is. There's a lot of don't knows in this argument, but it's a kind of negative argument which says that, okay, understanding is something other than a computational process, and we see in the laws of physics, up to this point, only computational processes. So you see in the physical laws, Newtonian mechanics, in general relativity, in Maxwell's equations, even in the Schrödinger equation, you see something which simply follows a computational process. So if there's something in physics which goes outside that or goes beyond it, the place to look is in where quantum mechanics doesn't go quite right. When I say quantum mechanics, the trouble is that people interpret quantum mechanics, I think my colleagues on left, right, which is the left-hand side of the audience, are taking the probability aspect of the theory as much more basic than I am. You see, I regard the probability aspect as somewhat secondary. That the basic thing is how the evolution takes place according to unitary evolution and according to quantum mechanics, the Schrödinger equation. And these things is where you see this extraordinary precision in the way the theory operates. When you get outside that, you just have probability measures in the collapse of the wave function. We need a better theory there, and that better theory would lead to some comprehension of what's involved in understanding things. And I think that's a huge leap. We're certainly not anywhere there yet.
Okay, thank you.
Last question.
This is a proposition for the panel to comment on, okay? So I would say that if we consider the word now for the now moment, yeah, we could perhaps put a cognitive now in one category, a mathematical now as in t in the short, in the wave function, a physical now in the sense of what kind of now we're measuring when we entangle two photons by spontaneous down conversion, for example. You know, because there is light and there is light traveling, and we say that these photons are entangled because they may happen here or here in different crystals. Yeah, so those photons we measure because they're close to each other in correlation. It's what we call entanglement. Yeah? So that's the physics time, very small. And then there is another kind of now, which I'm going to propose, has to do with the development of a soul. The cognitive processes, the mind and the soul, are going to be shaping the cognitive processes. So the way I perceive the now in the jungle, maybe 5,000 years ago, if I can translate myself there, would be the tiger is coming. That's my immediate boundary after the now. The tiger's coming. It's in the past now. I look for an alternative over there. If I forget about the tiger to be in the now, in the mathematical now, I'm dead. So that cognitive moment is different. If I'm an enlightened person, I may talk to the tiger and appease the tiger. That's a completely different cognitive now. So my question is, wouldn't it be appropriate to just differentiate the categories between the nows that we're talking about, from the decision analyst point of view or from the experimentalist in the quantum physics lab? You're characterizing a utility function here. You're trying to measure an eigenvalue here. And the probability tree, it's dynamically changing in terms of quantum mechanics, unless you change the probability tree of the decision maker, the subjective probabilities, moment by moment. So there are relationships here, and there are different kinds of now. That's my proposal.
I think now is the time we end the sessions.
Right.
Let's thank our speakers and a great audience. You guys have been awesome hanging out here. Concurrent sessions begin at 5 p.m. Then I think there's a poster session, and then I think Harold's buying drinks for some people. So thank you all. See you at the concurrents and posters. Thank the panel.